Okay, so what I was thinking of doing today is based also on Hansel feedback on office hours and what I've seen in my own office hours. I was going to just go quickly over 3 of the main mistakes that people make in this part of 201 to just make sure that these are not things you're going to do right on the quiz, or at least you understand that these are problems and you think back to that and try to sort out things in your mind, okay? I'll list these 3 major problems that I see in general. And then after that, we can go, and if this doesn't cover what your problems were, we can go into actual questions and answer things in which you ask me specific questions that are not clear yet in your mind, okay? All right, so, okay. So what are the main issues that I see time and time again? So the first issue has to do with composite bars. So if you have, say, a bar made of, maybe the top is made of aluminum and the bottom is made of steel. And you have a bar like that, composite. And then you have a load applied to the bar. One thing that happens all the time is that people have issues figuring out what are the stresses in the bar. So there are different kinds of mistakes. So say that you have area of the aluminum, area of the steel, and then you have E of the aluminum. Let me call it A and S so that I do not go crazy. A of the aluminum, A of the steel, E of the aluminum, E of the steel, so that the sum of these areas is A. So A is the whole cross-section. So mistakes. So wrong thing. Wrong. If I take the force, the whole force, and I divide it by the entire cross-section, I get an average stress. I do not get either the stress in the steel or I do not get the stress in the aluminum. So if you tell me F over A is equal to the stress in the steel is equal to the stress in the aluminum, that's not true. You cannot just take the force and divide by the cross-section for a composite bar and get the stress in either of the material, because the stress is going to be different in the 2 materials. So obviously, this is the wrong path. Another thing that I see happening is you take the force and you divide it by the area of the aluminum, and you say this is the stress in the aluminum, and you take the force and you divide by the area of the steel, and you say this is the stress in the steel. This is also very, very, very wrong, because what you're saying is that the aluminum takes it all and it has this stress. Then the steel takes it all and it has that stress. That's not the way things work. Together, they give you F. Not each by themselves gives you F. If you do this, then you're going to get 2 Fs together. You see, this is wrong. So this is bad, bad, bad stuff. You don't do that. The correct way to do it, correct, is you take the force, you divide it by area of the aluminum, E of the aluminum, plus area of the steel, E of the steel. What does this give you? The strain, right? The strain. This tells you the force is carried both by the aluminum and by the steel together. And then after you get the strain, then from the strain you can get the stress in the aluminum equal to that strain times the E of the aluminum. And the stress in the steel is equal to that strain times the E of the steel. You see? This is correct. This is wrong. We good? Do you have any doubts on this stuff? No? Good? OK. So eliminated problem number 1. Problem number 2 The second problem has to do with what happens so it's the connection between strain and elongation. If I have a bar like this, in which I have a variable cross-section, I can have a bar like this, or I can have a bar that is like that, something in which the cross-section is not homogeneous. Or I may have a bar which is made of one material up to one spot and another material after that. So I have one material here and a different material here. If I apply a force to these bars, force, force, and force, and they get a certain elongation because of the force, delta. So this elongates by delta, and this elongates by delta. But I have different cross-sections at different spots, or I have different materials at different spots. Then a very wrong thing to do, wrong. The strain obtained as the elongation divided by the total length of the bar. So if these are all bars that are long, have length L. I cannot just take the elongation at the end and divide it by the original length of the bar to get a single value of strain. Or the other way around, I cannot get delta by saying is equal to some value of strain times the length of the bar. Can I do that? Why not? Why can't I do it? Why?
The strain is a function of x, so it's not...
Exactly right. There is not one single strain. The strain changes from spot to spot. Where it's thin, it's going to be more strain. Where it's thick, there is going to be less strain. More strain here, less strain here. If this is soft and this is hard, the soft one is going to strain more. So there is not one single strain in these problems. So you cannot simply do that, right? First, you need to find the strain as a function of x, and that's going to be equal to the axial force divided by the EA effective of x. And then you can obtain the elongation by integrating the strain in the x. There is no shortcut. There is no easy, I don't need to do the integral. You have to do the integrals. Okay? Because strain is not a constant. Strain changes from location to location. There is no easy lunch. Okay? You gotta eat your vegetables.
But the strain is the same everywhere.
When the strain is the same everywhere, then you can do the shortcut. So if I have a bar, so in order for the strain, for this thing here, only works, this is only if you have a bar with constant cross-section, constant E, and constant axial force. So if you have constant cross-section, constant E, and constant axial force, so that this is not a function of x, and this is not a function of x, then of course this is going to be a constant. So a constant times the x is the constant times L, and you recover what's on top here, okay? But that is the absolute only case in which you can use this shortcut. If the force changes, the area changes, the material changes, But
then once we do the axial force over EA effective, that strain right there is the same everywhere. And then we can do
no, this strain is a function of x.
Okay.
It's the same everywhere on the cross-section. So say for instance that I have a composite bar like this, right? At every point on this cross-section x, each of these points on the cross-section will have the same strain epsilon A of x on that cross-section x. So the strain does not vary on the cross-section. So if I look at the cross-section and ask, what is the strain here, the strain here, the strain here, at a certain x, so I'm looking at x. At this x, I have epsilon A of x uniform on the cross-section. So that's where epsilon A is constant, on the cross-section x. But it varies from point to point along x. It's a function of x, and only of x. Good? Okay. third problem. The third problem came to me from Hansel from office hours. And after he mentioned it, I realized that this is something that I've seen over and over in exams. So that's another thing that you have to be extra careful about. All right, very simple problem. I have a bar like this, uniform cross-section of length L. I have a force at L over 2, F1, and I have a force at L, F2. Okay? And this is just as cross-sectional area A, modulus E, and this thing has a length L, and this is L over 2, and this is L over 2. It seems fairly simple, right? There is one thing you have to be careful about. Okay, so let's just do step by step. The first step is we obtain the axial force as a function of x. So the axial force as a function of x, from here to here, we only have to carry F2. And then from here to here, we also have to carry F1. So my axial force as a function of x is discontinuous. So here I have only F2, and here I have F1 plus F2. Okay? I'm going to continue that way, but imagine that all of this is aligned. Okay, so now I do epsilon A of x. So epsilon A of x, I divide the axial force by EA effective, and in this region here, I'm going to have F2 divided by AE. EA effective is just area times the modulus. In this area, in this region here, though, let me put it this way, I'm going to have F1 plus F2 divided by AE. So my strain is discontinuous. No big deal, you say. I can deal with that. Okay, so what we want to do next is we want to calculate U of x, Ux of x. And so you start totally fine, because you say, okay, I know how to do it. Ux of x is going to be not the same here and here because the strain is different. So you know that you need to split it up. And then you split it up and you say, let's start from 0, x, L over 2. So let's figure out the displacement in this part of the bar. Okay, you say this is U of 0, because I know that the displacement is going to be 0 at the wall, plus the integral from 0 to x of epsilon A of x. That is F1 plus F2 over AE in the x. Okay? I get U of x. Now, where there is a problem sometimes is in the Ux of x of this part of the bar. So let's make a picture of what happens to the bar. We see there from the U of x that this bar, say that I paint this part here of the bar like that. I paint it, and I see what happens to it. Well, that part there displaces by that U of x. It's going to be a linear F1 plus F2 x. So this is going to be equal to F1 plus F2 over AE x. Right? So I can start plotting things here, and I have something that looks like that. Linear in x, and up here, which is U of L equal to U of L over 2, I'm going to get F1 plus F2 L over 2 AE. Okay? All right. Now, this is what's happening to this bar then. It moves forward, and this spot here, there was a L over 2, has gone all the way up to here. If you were a part of the bar that was right next to it, what can you do? Can you just stay put? say that this guy here, let's call it Jim. Okay? That point of the bar is called Jim. What is Jim going to do? Can Jim stay with displacement at 0? It can't, right? Because this whole part of the bar is pushing Jim to the right. So when I integrate u of x on this other part of the bar, it starts at u of L over 2. It starts there. And then you integrate from L over 2 to x, this train here, F2 over AE in the x. So this part here, you know, it's F1 plus F2 over 2 AEL, and then plus F2 over AE x minus L over 2. When you do that, what happens is that you start here with your displacement, and then you go up with a slope which is a little less than the other slope, because you see this is the derivative of that. And so you're going to have a displacement field that looks like that. You see here, it's the derivative. So ux can have discontinuous derivative. And that is OK. So the derivative of u of x can be discontinuous. But can u of x itself be discontinuous? Can I have a u of x if instead of putting u of L there, I had put 0? So wrong. Wrong. If I said u of x is equal to u of 0 plus the integral from L over 2 to x of F2 over AE in the x. If I had done it like that, my u would have looked like that. It would go up to L over 2, and then it would start again here and do that. This tells me that this guy to the left of Jim, Charlie, has moved up to here, and Jim has stayed put. And they occupy the same space. They can compenetrate. If you find the u of x that has discontinuity like this, you did something wrong. If you find the u of x that has a discontinuity like this, what does that mean? What is that? It's a hole. It tells you that this bar went up to here, and then this bar starts here. And you got a hole in the middle. Discontinuities on u of x are very, very bad. Holes, cracks, compenetration, not allowed. U of x is continuous. And when you integrate it, think of your bounds. Okay? For this part of the bar, this is the place where I know u of x. I know it because I calculated it by integrating this part first. So again, u of x is u where I want it, is where I know it, plus the integral of strain from where I know it to where I want it. But I can know things also in the middle if I've integrated it before on the other side. Okay? You do not need to start from the wall. We're good. Okay. Is there anything else? I mean, is this okay? Is this useless, or is this something that actually helps? Yes?
If there's a wall on the other side too, then would you also have...
Brilliant question. Brilliant question. Absolutely genius question. What happens if I had a wall on the other side? If I had a wall on the other side, I can cheat. I can cheat a little bit because I know something else. Right? If I have a wall on the other side, and I have the same problem like that, right? Then I can say that u of x is equal to u of 0 plus the integral from 0 to x of epsilon a of the left side. I'm going to call it left of x in the x, And this is for 0 less than x less than L over 2. And on the other side, I can do either what I did up there and say u of L over 2 plus the integral from L over 2 to x of epsilon a to the right of x in the x. Or I have another choice because I know something else. I know that u of L is 0 in this case. So in this case, I can cheat and start from here. So I can say that I can write that u of x is u of L plus the integral from L to x of epsilon a to the right of x in the x. And both of them are true for L over 2 less or equal than x less or equal than L. Actually, there are discontinuities, so let's leave it open. Okay? So if I have a wall on this side, I can cheat and start from the other end, because this one now is 0, and I know it, the same way as this one is 0. Okay? Good? We good?
But for the one above it, do you not have to add the u of L in, like, it would be u of L plus?
For the one above it, I'm going to have a u of L. Here it is. That's just going to be the value of this function for x equal L. If I put x equal L here, L minus L over 2 is going to give me L over 2. So I find that the whole displacement is going to be F1 plus F2 over 2AE plus F2 over 2AE multiplied by L. Okay, so that's going to be this displacement at the end that happens to be equal to delta, the way that the thing is set up. Okay? If you wanted, you could first calculate delta, and that would be your u of L. And then you would have u of L, which is delta, plus the integral from L to x, and you can start from the other side. But if you start from the other side here, and you're integrating your u, you need to know where to start here, and that's now 0. That's u of L. So if you already calculated it by calculating delta, I'm totally fine if you want to go backward from there. And then your u of L, in that case, will be delta. Okay? If that's not clear, we should go back to basic integral kind of stuff. Okay?